Okay, so we are going to start chapter 8 about estimation. So this chapter is maybe the statistics you have imagined, because we are making inference using data, and we calculate an estimator. That's basically what you imagined, what you how you see the statistics in general, right? So, but before defining estimation, I'd like to set up the basic framework, how to how to make statistical inference. It is like the relationship between what we want to know and what we have. Right, what we have is data. This is simple, but what we want to know must be discussed a little more, and we are going to start from the very beginning, a very simple case like this. So imagine the presidential election prediction. So we would like everyone is interested in that. So it's a good timing, like it. So I don't know if you watch this video before or after this election, but anyhow, assuming that we are trying to predict the election outcome, and first imagine if you could now I'm recording it in October. So if you could meet every voter and ask about who they are going to vote or whether they are going to vote, if you can do that for every voter, then it's not statistics. You know the answer. Then it's simple computation, right? If that was possible. If say like uh, say the New York Times can spend a lot of money and people and just ask everyone to tell their willingness who to vote, then it's not a problem of statistics because we know everything. However, the problem is we cannot observe everyone's votes, right? Like typically due to time constraint and financial constraint, budget constraint, we cannot it will cost a lot of money, and maybe it is impossible to do the survey within a month, right? So here comes the distinction between the population and the sample. So the population is all the voters, right? Ideally, we would like to observe every one of them, if possible, but because we cannot observe all of them, uh, they are the population, we cannot observe all of them. We instead observe just a part of them. That is the sample, right? The sample is the set of observed objects from the population. So instead of observing every voter, we surveyed, say, 1,000 representative voters, right? I mean, random voters. Like 1,000 is the sample. But the population, I don't know how many voters there are, but we can just assume there are infinity. That's not a problem. Anyhow, we cannot observe all of them. So there is a bigger set population. That's what we want to know, but we cannot observe them, so we only observe some part of that. So basically, statistics and especially estimation is about their relationship. We would like to state the relationship so that we can expand our information from our observations about the sample to the larger set, larger population. Okay? So that is what we learned in random sampling. In random sampling, what we want to know is so in random sampling, we studied the relationship between the distribution of a single outcome. But from there, we survey multiple outcomes. We observe multiple outcomes, like multiple dice or survey of annual income. And then we studied the distribution of the average based on our observed outcomes. So we studied how the sample is distributed based on the population, right? So this process is random sampling. We generate sample by random sampling, and we learned how it behaves. Now, so that is purely theoretical. We learned central limit theorem, we learned low large numbers, and we learned some properties about the mean and the variance. We needed them because we are going the other way. Actually, what we observe is the sample, but what we don't observe is the population, right? In theoretical analysis, it's usually going the other way. We assume that as if we know the population distribution, like dice simulation. I started from one special dice and I simulated the distribution of like 25 dice, right? But that's simulation study, which is not realistic. In real world, we cannot do that. What we are more interested in is we observe, like say, dice results, and from there we'd like to study what is the true distribution. If the dice is fair, or if this dice has any problem, what was the original distribution? So it is going the other way. That is statistical inference. So we are going to make statements about the population based on the sample. That's what statistics does, right? For example, what percentage of voters support candidate A, right? So, if you want to answer this question, then first you have to understand the random sampling, how your survey works. That was random sampling distribution. But now and after you understand that, we can utilize that information, that knowledge, that theory to make a guess. That is the following chapters in chapter 8 and 9 and 10. Okay? So, like we distinguished the population and the sample, the population is basically what we want to know, and the sample is what we observe. So we make those distinctions. And similarly, we distinguish like parameter and statistic in a similar manner. The parameter is a numerical measure that is about the population. So this is basically what we want to know. We want to know the parameter. It can be mean, median, variance, probability, whatever you are curious about. Whatever you want to know is called the parameter. And to know the true parameter, you need infinite observations. You need to observe everyone. So I will simply call them infinity, right? So you need to observe everything, everyone included in the population, which is like infinity, not possible. But point is, the parameter is what we want to know. On the other hand, a statistic is a numerical measure calculated from the sample, right? It can be also mean, median, variance, probability, whatever you can calculate. But the difference is it is tangible. You observe it. Like it is based on your observations. So you have a specific number, right? Concrete number. So in the end, what we will do is we first set up what we want to know, that is a parameter of interest, and we are going to find a statistic, what we calculate from the data, to make a guess about the parameter. So we will choose the best statistic that to estimate the parameter. That is basically the statistical inference, right? That's the basic setup. So now it is clear what these guys are doing. Parameter, what's the parameter? What's the statistic? So parameter is first unknown. The basic properties of a parameter should be unknown because it is our target. We are going to guess about the parameter. So of course it is unknown. If it is known, then you don't need to learn statistics. You don't need to use any statistics to guess something is known, right? Does not make any sense. So it is unknown, what we want to know. And so it is the target of any statistical inference. We are going to target a parameter. So usually it is denoted by theta in generically. Theta, Greek letter, theta is often used as the target parameter. On the other hand, a statistic is random because it is calculated from your data, and data is generated from a random sampling. And random sampling, so it follows a sampling distribution. So random sampling is random, so your data is random. So what you calculate from the data is also random. Randomness remains. So this is what it's the means of the statistical inference. You are going to use a statistic to make a guess about the parameter, right? So usually we denote it as theta hat, right? We call this theta hat. So that means we would like to know theta, so we calculate theta by theta hat, right? I am curious about the expected, like the mean annual income of an adult or of a, like say, economics major. I'd like to know the expected initial salary of an economics major college graduates, and then we observe some salary data and calculate something. That is, the calculated result is denoted as theta hat. The true expected salary is theta. Okay, right. So let me then think more about the detailed inference methods. There are two main inference methods. One is estimation, and the other is hypothesis testing. Estimation is a neutral way of guessing. Like, it's literally open question. Like, what percentage of voters support candidate A? Or what is the mean gas price of gas stations in New York State or Manhattan, right? So it is an open question. You can answer like any number, 0, 10, 100, like 50%, whatever, right? There is no hypothesis, no like assumption. However, hypothesis testing is a little bit weird in some sense because you have a hypothesis and it is a yes or no question. So you are testing if your hypothesis is correct or not. So it is different. For example, it's like, so previously in an estimation problem, your research question is like, what percentage of voters support candidate A? But in a hypothesis testing problem, your question should be a yes or no question, like, do more than 50% support candidate A, right? Something like that. Is the mean gas price in New York City lower than $3 per gallon or not? Is this correct? Yes or no, right? So hypothesis testing is a yes or no question, but the estimation is an open question. So that is a simple way to distinguish them. And this chapter, we are going to learn estimation. It is more straightforward because it's open question. And in chapter 9 and 10, we spend 2 chapters on hypothesis testing because it's like there is a nuance, like it's more subtle, right? So testing requires more discussion and some preliminary things. So we are going to spend more time on hypothesis testing later. Okay, so then let's think more about the examples. Presidential election. The population is all voters, and the sample is survey respondents, right? And the parameter we are curious about is the probability of voters supporting candidate A. And a statistic, what you can use as an estimator is the probability of respondents supporting candidate A, right? So, and like the difference is for all voters, you don't observe all voters, so you cannot calculate the parameter unless you observe all voters. But statistic is based only on the respondents, which is just a part of the voters. Okay, so you can think about the presidential election as an example of estimation problem by matching those terms like this. And also gas price in New York City, like the population is all gas stations. If you can visit all gas stations in New York City, then you can just collect the data and calculate the mean gas price. That is just a matter of computation if you can do that, if you can observe them. But it's impossible, assume that it is impossible to visit all gas stations. So our sample is limited to observed gas stations, right? Observed gas stations are just a part of all gas stations in New York City, randomly chosen ones. And in this case, our parameter is mean gas price of all gas stations, right? When I say mean, it is true mean, which is based on all gas stations, but we cannot observe all gas stations, so we calculate mean gas price of observed gas stations, right? That is a statistic because it is observed, but the parameter is unknown, what we want to know. We want to know the mean of all gas stations, so we used a statistic as an estimator to guess the unknown parameter. Okay? So then think about this. Suppose that you are an electric vehicle manufacturer and you just received a shipment of batteries from battery maker. You are inspecting the batteries, and you can also think this as a kind of estimation problem, right? Because you cannot inspect every battery. What is not correct? If you understand like quality control, inspection as an estimation of the defect rate. What is not correct? Population, sample, parameter, statistic. Okay, the answer is E, right? All are correct because so literally we would like to, if possible, we would like to check every battery if they are good or bad, right? But that is not possible given the time limit and the cost is too high. So we randomly choose some batteries and inspect them and see if there is any common problem. So that is the sample. Randomly chosen batteries that are inspected. They are sample. What we want to know is the parameter, that is the probability of defective batteries among all batteries I received. Among all, that's the point. We do not observe all batteries, so we calculate a statistic which is the probability of defective batteries among inspected. So those that are inspected are observed, so you can calculate the probability among inspected. So this is exactly another example of estimation. Okay, now then, let's think about a parameter more carefully. So you can imagine different types of estimation problem. So then I will ask a seemingly weird question. What is not a parameter? A, standard deviation of life expectancy. B, expected increase in sales after a price cut. C, total number of heads when you toss 10 coins. D, difference in mean gas prices in New York and California. E, conditional probability of making a second free throw after making the first. Okay, so what cannot be a parameter? Or you may put the question like this. If you think about an estimation problem based on these, what is not statistically possible? What you cannot answer, right? Think about it. So how can you answer this question? The simple idea is first, so a parameter must be should be able to we should be able to calculate the parameter if you observe everything. That is the definition of parameter. If you could observe infinite number of observations, you should be able to calculate the true parameter. Like for example, if you observe the life expectancy of everyone on Earth, then you can calculate standard deviation. That is possible. And B, expected increase in sales after price cut. If you can do this infinite times, if you can repeat the experiment infinite times, of course, in reality, it's not possible, but in your imagination, if you can simulate that, you can calculate the expected increase, right? And D, let's think about D first. If you can observe all gas stations in New York and California, you can calculate the difference in mean gas prices. That's possible. Finally, conditional probability of making a second free throw after making the first. If you repeatedly do a free throw, or if you observe all the free throws in basketball history, then you can calculate the conditional probability. So A, B, D, E can be calculated if you observe everything. However, C, total number of heads when you toss 10 coins. So you have 10 coins and repeatedly throw 10 coins again and again and again. The problem is the total number of heads is random. It's different. So in your first experiment, it could be 0. In the second experiment, it could be 10. Like it can be any number between 10 and 0. So there is no fixed answer. There is nothing to calculate. It is something that random. So C cannot be a parameter, right? So again, for something to be a parameter, it should be fixed. It should be non-random, and it should be calculated when you have infinite observations. But number of heads is something purely random. No matter how many times you repeat, it will be different every time. So it cannot be a parameter. It would be better if you write it as so. For example, you could estimate the expected number of heads. If you change the phrase as to expectation, mean number of heads, right? Then you can estimate that, but just simple random number cannot be a parameter, cannot be estimated. So then on the other side, so, parameter is pretty simple. You can just choose what you want to estimate. That is the first step of an estimation, and which is usually obvious, trivial. The only thing you have to worry about is this one. It is random. Then it doesn't work. As long as you can calculate something when you observe infinite observations, then that can be a parameter. But bigger problem is how you estimate that. What is an estimator? Which estimator is the best? That is a different scenario because there are many possible candidates, right? For example, I'd like to estimate the expected value of X, like expected value of heads, expected number of heads from 10 coins. What can you use? You can use sample mean, from your experiments, or you can use something very interesting, sample mean after deleting the minimum and the maximum, right? So outliers are deleted and calculate sample mean after deleting outliers. Or you may use sample median. These numbers may capture something similar, so you may argue that they are reasonable estimators, right? So, but here, for now, what you need to think about is an estimator must be able to calculate it based on the sample. And we are going to use it because we are going to use it to estimate a parameter. Parameter is unknown. Then your answer must be something known, right? That is an estimator. Okay, so let me ask you another question about the estimator. Now, I want to estimate the mean gas price in New York City using 100 gas station observations. I have 100 observations. I don't know how many gas stations are in the city, but suppose infinity, but I only have 100 of them. Then which one I'm estimating mean gas price, but which one you cannot use as an estimator, right? So The question is clear. What is the mean gas price? And now you have to find an answer. But what I'm asking is, one of these cannot be an answer. Right? I'm not asking about what is wrong or what is right. Or what just simply does not make any sense. It cannot be an answer. So, think about this. A, any number came to your mind, such as $10. I just chose $10, for no reason. It is just I just came up with this. I just make a guess just without looking at the data. B, half of the sample average, right? You can write like this using our notation: x bar sample average divided by 2. C, sample variance. And D, population mean. E, the gas price at the nearest gas station. I don't wanna see all the numbers. I just choose the nearest gas station's number, and that is my estimator. That is my answer. So among these 5 candidates, simply one of them is not an estimator. It's not a valid answer. What do you think? This question is a little bit tricky. The answer is D, because population mean is unknown. So when I say population mean, this is the mean calculated from the population. And again, population is everything. Every gas station in New York City. We don't observe them. So population is not available to you. So you don't know what is the population mean. So it's like basically that is what you want to know. I am asking, my question is, what is the mean gas price? Then your answer cannot be the mean gas price. So basically it is the same thing. Mean gas price in New York City and the population mean is just same thing. You are just saying the same thing again, so it's not a valid answer at all. At least all the other things can be, the other answers are usually wrong, but anyhow they are a number, right? So you ask me what is the mean gas price? Well, I may say $1 million per gallon. It is wrong, obviously wrong, but at least it is a wrong answer. But D is not even an answer at all. So you cannot tell if it's right or not because you cannot calculate that. So this is the first thing you have to think about when you do an estimation, right? So first I said the target must be something fixed, so that we can make a guess about that. And second, you have to find something that is available to you to make a guess about that, right? The target must be fixed and your answer must be calculatable, right? That they are really, really basic requirements for estimation, but often they are ignored. So I wanted to emphasize what's usually missing. And now we understand our target, and our answer can be anything we can calculate. Then the next step is to find a good estimator, to think about what is the best estimator among anything we can calculate, right? So there are unlimited number of numbers we can use as our answer, but then what is the best? To answer that, we need to use statistical theory, the random sampling, the sampling distribution theory. Okay, so we are going to do that in the next video. I will give you 2 criteria. There are multiple criteria, but I will introduce 2 criteria, basic criteria for an estimator to be good, right? Okay, thank you for watching, and I will see you in the next video.